Lecture 3.1, Chapter 3, Section 5, Static, Stagnation, and Dynamic Pressure. First, a quick review. This figure at the beginning of Section 4 does a nice job of showing you the two versions of Bernoulli's equation, sometimes known as Bernoulli's integral. The version along the streamline is, in my experience, by far the more common. The one normal to the streamline not used as much, partly because getting rates of curvature R is not so easy. But before we zero in on the along streamline case, let's look a bit at this second less common case. So I want to start by having you go to page 112, which is 104 in the 6th edition, to example 3.5. And I'd like you to work your way through that. There's not a whole lot there, but if you work your way through that as best you can, if you're not quite sure what to do, just keep going and come to a conclusion quickly, then I'll talk you through it. So I'm going to pause here and let you do that. Okay, you will have noticed that this problem's final answer is symbolic, without values for the variables. Now, getting values for density is easy enough, and for height, of course, and we'll spend most of our time today hammering out a method of getting velocity, but I am unaware of any radius of curvature measuring device, surely no common one. In any event, though, there are some good points to be made looking at this example. First, if you look at the more common along the streamline situation, you get a pair of equations here. One, which is the first answer in the problem 3.5, follows a streamline from 1 to 3. You get an identical looking one following the streamline from 2 to 4, of course. Think for a moment about the pressures 2 and 4. He says their free surface P equals 0. What that really means is that, or the implicit argument in that, is that the air density from 2 up to the height of 4 is much less than that of the water, factor of 1,000 about. So neglecting that pressure decrease due to air is negligible, and because the pressure term occurs linearly, plus P, that atmospheric pressure just drops out. So we routinely set the pressure at the surface equal to 0, and you'll see that next time, by the way, on Thursday's lectures. That will occur a couple of points, and a couple of important points. Now, let me try to get back on target here. Oh, right. Now look at points 1 and 2. Now, to be sure, I'm no longer looking along streamline, I'm looking cross streamline, but I'm looking cross streamline in a place where everything's level, there are no accelerations, meaning there are no forces. Meaning the forces are in balance, which means that at point 1, the vertical pressure gradient must just balance the vertical force due to gravity, which is nothing more than the hydrostatic relation. Go back to page 44, 42 in the 6th, and just look at that. I'll pause for a second here. Okay, now back to page 112, 104 in the 6th. This time, finally, go between points 3 and 4. Now here, the water is accelerating around a curve. So, in fact, both its speed and its direction are varying. Now, to make that happen, we need some forces. After the speed drop, V4 is less than V2. This is simply a trade-off between kinetic and potential energy. We're back in dynamics 221 territory here. So the variation of the velocity term is something that you've already seen quite a bit. But now, finally, look at the cross-stream version of Bernoulli's equation. In other words, the end of this example, and look at his solution. Take 2 points, 3 and 4, which you think are probably normal to every intervening streamline. So from 3 to 4 is, as a matter of fact, legitimately a cross-streamline case. And check that the solution you see in the second answer in that box makes sense. Okay, that's as far as I want to go with this example. Now let's get on to the main show for today. And this figure, which is just the beginning of your section 3.5, has a characteristic step. We bring the flow to a halt at 2. So, whoops, sorry, didn't trigger that. You're going to have flow at point 1 moving along at the free stream velocity of v, and then you're going to come to some point P2 where it comes to a halt. The columns little h and capital H1 we assume are constant. In other words, what we're assuming is the flow's been set up, it's steady, nothing's really varying. You've got flow moving, but everything is at any given point constant, so it's a steady flow. Which means, by the way, we get to use Bernoulli's equation in the form that we've derived it. So this is not a small point. You've got to have steady to do what we've been doing. So doing that, all you're going to do is say that the pressure at 2 is greater than that at 1. Okay, so you're going to subtract, you're going to take, I'm not saying this very well, along a streamline from 1 to 2, at 1 you've got the Bernoulli terms, at number 2 you get the Bernoulli terms, and you're just going to solve for v. And here's what you get. It's very straightforward. And this is the equation which is why a pitot tube works. I don't know how many of you know what pitot tubes are. If you know anything about airplanes, you know what pitot tubes are. But they simply use this feature to get air speeds. And they work pretty well. So despite all of our harumphing about making sure you've got all your assumptions taken care of, in fact, it winds up being pretty robust. Now, as engineers, of course, it's going to be your job to make sure in a real case that indeed those minor effects are not important. That's what you get paid for. But in fact, at the end of this section, Munson spends some time talking about things that can throw this off. Looking at this equation, you can kind of guess part of what they are. If, for instance, you're traveling close to Mach 1, then you're going to have density variations. Well, I can't have a constant density anymore. And so on. If there's a lot of loss, if there are viscous terms, you're going to lose energy. There are a variety of ways that you can have this equation go south on you. The surprising thing is, it holds up pretty well. So this is the main point of this section. Now next time, Thursday, what we're going to do in section 3.6 is take Bernoulli along a streamline and apply it to a variety of cases. So this first case that we're working through slowly, solving velocity, is a first example case of what you can do with Bernoulli along a streamline. And that is the end of today's lecture.